So I think we can probably go ahead and get started, particularly since Sarah is going to deal up front with the questions that were submitted beforehand. I'm Rob White, and I'm Williams' Alumni Communications Director. And we all know that this is the Physics of Musical Sound with Sarah Bolton, who is the chair of the Physics Department and Professor of Physics at Williams. As I just mentioned, Sarah will contend with the questions that were submitted in advance to begin with, and then we can open it up to a conversation that takes account of other questions you might have in mind or questions that come up.
Great. Okay, so there were 3 questions that were sent in to begin with, and actually 2 of them are very closely related to one another. So let me just summarize what those questions were and try to answer them. And then when I'm finished with those questions we got in advance, I'm very happy to answer any other questions that you might have. So the first question came in from David Wooden, and it had to do with the harmonic spectrum of the human voice, and in particular the way the sounds produced by the human voice compare to those produced by musical instruments. And the question that turns out to be closely related to that was the question sent in by John Calkins, a really interesting question having to do with trumpets, and in particular how the sound of the trumpet is altered when you insert different types of mutes into the bell of the trumpet, which both make it quieter and, as John points out, change the character of the sound. So I wanted to address both of those together a little bit because, as you may know, the human voice and the trumpet have in common that they work by creating vibrations inside a tube of air, right? So the human voice, you have the tube of air that's produced by your throat and that's shaped and defined by the way you open and close your mouth and the way you move your tongue around and shape that whole vocal tract. And the trumpet, obviously, there's the tube of air that ends in the bell, and it's not as flexible as the human voice unless you try to stick something in the bell, like a mute, which is, in fact, a lot like adjusting the shape of your mouth to change your voice. So the particular question that David asked was, how does the harmonic spectrum of the human voice compare to that of musical instruments? So just as a reminder, any long tube of air has a particular set of sounds it produces that we call the spectrum. The spectrum tells us what frequencies of sound, which corresponds to what pitches musically that tube likes to vibrate at. And the things that determine which frequencies of sound, which also has to do with which wavelengths of sound are produced, are the primary thing is the length of the tube and what's happening at the 2 ends of the tube. So if the 2 ends of the tube are both open, like they would be if you hold your mouth open, if the 2 ends of the tube are both open, then the lowest sound that you can make, the lowest pitch that you can make, is determined by basically twice the length of the tube. So I think that might be something Elise was referring to. The longest wavelength is twice the length of the tube, and then to find the frequency, you take the speed of sound and you divide by that wavelength. So it's the speed of sound, which is about 300 meters per second, divided by twice the length of the tube. So if the length of the tube in your vocal tract might be 1/10 of a meter, then you would get a longest wavelength that would be, let's see, 300 divided by about 0.2. So what does that have to do with the spectrum? So the spectrum happens because that tube can vibrate at a whole bunch of different frequencies, all of which are multiples of that lowest frequency. And so if you could produce, let's say, a sound wave at 20 hertz, that means that the air is sloshing back and forth 20 times a second. You could also produce one at 40 hertz and also one at 60 hertz and also one at 80 hertz and also one at 100 hertz. And as I talked about in the videos, when somebody gets their throat vibrating so that it's making a sound with all of those different components in it, we don't actually hear a chord, right? Because I think most of you out there don't know how to sing a chord, right? Don't know how to sing more than one note at once, unless any of you are tube and throat singers, in which case we can talk about that. But otherwise, when you make a sound by shaking your vocal cords, it shakes that tube, and you get a a bunch of these different harmonics, a bunch of these different frequencies all vibrating at once. So the original vibrations are created in our vocal cords, which are floppy pieces of flesh in our throat, and then they vibrate in this tube of air. And those vibrations are affected both by the cords and by the resonances of the tube, by the frequencies at which the tube would like to vibrate. Okay, so how does it compare to musical instruments, and is it constant or variable? So the harmonic spectrum produced by the human voice is definitely variable. What the vocal folds are doing, your vocal cords are doing, is variable because you can make them tight or loose. And as you know, if you've ever played a string instrument, by tightening or loosening the string, you change the note that it would like to make, right? So you change the frequency at which it would like to vibrate. So that's one way it's variable. If you want to change the pitch you're producing, you change how tight or loose your vocal cords are. So that's one thing you change. But then you also know that if you're going to sing a particular note, let's say you're going to try to sing a C, you could, if you were an opera singer, also try to make that C correspond, let's say, to a particular vowel sound. You could try to sing ah or oo or e. And hopefully if you're all trying this with me over the phone, you're going ah and oo and e, and you're noticing that you're changing the shape of your mouth to make those different vowel sounds, right? So when you change the shape of your mouth, you're actually changing the shape of the tube that the air is vibrating in. And so you're changing which frequencies the air would most like to shake at. So what happens is the vocal cords themselves will be happy producing this spectrum of different sounds. They might, let's say, if you pick a particular tightness, let's say they're going to be happy to vibrate at 20 hertz and 40 hertz and 60 hertz and 80 hertz and 100 hertz and 120 hertz. And those vibrations go out into the tube that is your throat. And then depending on how you've shaped your mouth, some of those frequencies will also be ones that the tube wants to vibrate at, and some of those frequencies will be ones that the tube doesn't want to vibrate at. And if you hit one that the tube likes, it gets amplified, so the air shakes more. And if you hit one that the tube doesn't like, it gets kind of pushed down, and so the air shakes less. So the whole spectrum is created initially in the cords, but then modified by the throat in a way that's completely dependent on how you shape your mouth. So if you look at the spectrum, the particular frequencies of sound that are produced when you're making an oo or an ah or an e, you'll see that they're quite different from one another in that, let's say if they're all at 20 hertz, one might have a lot of 80 and 100 and 120 hertz, and one might have a lot of 200 and 220 and 240 hertz. It turns out that the oo sound makes the simplest spectrum with mostly the lowest frequency and a little bit of the higher frequencies. As you go for the e, which you might think of maybe as an edgier or grittier sound, that corresponds to having much more of the higher harmonics, much more of the higher frequencies. So just to finish off the answer to this question, how does this in general compare to musical instruments? So musical instruments in general have the same basic components. They have a part that you strike or shake or blow, which begins the shaking that will create the sound. And then they have a bigger piece that's going to also shake, like the body of the violin or the brass part of the trumpet, let's say. And that part, with its own frequencies that it likes to vibrate at, its own resonance, will shape the sound. In general, the human voice tube does a better job of amplifying many of the higher harmonics. So not just the lowest frequency and twice the lowest frequency and 3 times the lowest frequency. The vocal tract often emphasizes the 15th or 17th or 20th harmonic, ones that are way up from the original low fundamental. Musical instruments are less like that. A flute, which is in many ways like the voice, has almost all just the fundamental frequency and a little bit of second and third and fourth harmonic, but you'll never see the 17th or 18th or 20th harmonic in there. The same thing is true for violin or a trumpet. The first 10 harmonics tend to participate in the sound and not much more than that. So the voice is particular in that it has a very low fundamental frequency. The lowest frequency produced by the tube's by the vocal cords is really pretty low, and then you're making a lot of use of shaping the amplitudes of these higher harmonics in order to be able to have speech, to be able to produce different vowel sounds that are easily recognizable. So, David, are you out there?
I am.
Did I answer your question?
In detail. That was fascinating. I've noticed over the years that this one particular experiment that I do with my voice, and I'm not going to do it now since we're being recorded, but if
you can. Come on.
Let me just try to describe it first. If you start with a kind of a low hum tone and hold it, it doesn't matter what pitch it is, but as you do that, if you just change the shape of your mouth from the vowel shape to the oo, I experience these buzzes, these resonances that seem to correspond with the overtones of the fundamental, and you can kind of hear them. If you practice, you can actually project them, so that other people can hear them too. I don't know. I'll try it once. If I sound goofy, it sounds something like this. Could you hear anything?
Yeah, but you're almost doing the tube and throat singer thing, right? So I completely hear what you're talking about, and those are overtones of that lowest sound that we hear. That actually, I think that the lowest sound that we hear is in general not even the lowest note that your vocal cords are making, because even when we're doing the ooh thing, we're still mostly hearing the higher harmonics. So, but yeah, you're absolutely right. As you change around, you get different resonances, and if you're trying to be really loud, you can feel it in different parts of your vocal tract, right? You can sort of feel it up in your sinus.
And if you learn where they are and you pause on those particular notes, you can get the whole frequency to. So those are mostly the higher harmonics then.
Yeah, those are mostly the higher harmonics, and actually there are various things that singers do to try to be heard. For example, over an orchestra. So if you have a whole orchestra with all these people playing, you might say to yourself, well, how does the soprano ever get heard over all those other folks who are playing the same note in principle, right? And this is another place where the fact that the vocal cords can do the high harmonics is helpful. So singers train themselves to do this thing called the singer's formant. Formant is the name for these amplifications of particular harmonics that happen due to the resonances of the whole tube and your whole head vibrating, not just the vocal cords. So they have the singer's formant, so they're adjusting the shape of their throat to really amplify the nearly the highest harmonics that we can hear with our ears. So up near the top of our hearing range, so that we'll be able to hear the singer's tone up above the instruments of the orchestra that are mostly using the lower harmonics of the same pitches. Does that make sense?
That's fascinating. Thanks. That's great.
Sure. You have to work hard to do it, so I can't demonstrate it. So I wanted to relate this a little bit to the question that John Calkins had asked, which had to do, as I said, with the trumpet and placing mutes into the front of the trumpet. So I don't know if anyone on the line is a brass player by chance. No. So if you've seen trumpet players play, they can generally, brass instruments are very loud, and we say they're brassy. They have this kind of edgy quality compared to, say, a flute, because the difference between a flute and a trumpet is that the trumpet does project more of its high harmonics really well into the room, and it does that by the shape of the bell, right? So the main difference that you would imagine if you were visualizing a flute and a trumpet in your head is that the flute just kind of ends at some point, and the trumpet has a bell shape. And what the bell shape does is it allows the higher harmonics, which are waves that shake faster and therefore have a shorter wavelength, so a shorter distance from one crest of the wave to the next. It allows those short wavelengths to make their way out into the room very effectively. And it's the presence of those high harmonics that make brass instruments brassier than say, flutes. So if you then take a mute and you stuff it into the bell, it does very much change the distribution of which frequencies are best projected out into the world. And in fact, there are different kinds of mutes, but one of them, which this John Calkins had particularly asked about, this Harmon Mute, is one that you sort of stuff into the bell, and it reshapes the end of the instrument so it's more like it's coming out of tube, a little bit like a flute, instead of out of something that gradually spreads out in size, like the bell of a trumpet. And so actually what that does is it makes the trumpet's set of harmonics much more like a flute. So it tends to de-emphasize most of the higher harmonics and make a gentler, softer sound. So as well as being a quieter sound, if you listen to a muted trumpet, you'll also notice that many people would describe it as a softer, more voiced sound. And that's because of the balance of harmonics that's produced when you take the bell and shape it in a different way. There's one particular mute that Miles Davis is famous for using called a Harmon Mute. And the Harmon Mute is actually used to create formants for the trumpet that work very much like the formants for the voice, the way that the vocal tract works to form the spectrum of the voice. So the Harmon Mute actually is made to sort of reduce the intensity of maybe the 4th, 5th, 6th, 7th harmonics or resonances of the trumpet, but amplify just one or two of the higher ones so that it gives the overall shape of the spectrum for the trumpet a shape very much like the overall spectrum that we get for the voice. And some people will say that this Harmon Mute makes the trumpet sound, again, more voiced or a little bit more like somebody singing. And that's because they've shaped the end in a way that's more like the way we shape our face when we're trying to make sounds with our vocal tract. So that's how those two things connect. So let's see. So the third question I was going to talk about was Mark Johnson's question, or perhaps this is Elise's question, or a question you put together collaboratively. Is that right?
That's right.
Are you there, Mark? Yep. So you had this question about what physical attributes of musical sound make the sound good to the listener. Is that right?
Mm-hmm.
Yeah, that's what you guys are interested in?
Yes.
So this is a really interesting question, and it connects a little bit to what I was saying about the trumpet and how it sounds brassy because it has many of these sort of 4th, 5th, 6th, 7th harmonics that are projecting really strongly out into the room. For a single note, we tend to say that a sound sounds smoother if it has just one or two harmonics in it, and it sounds edgier or brassier or sharper if it has more of the higher harmonics mixed in, so more different frequencies vibrating at once. So that's sort of for a single sound. Then if you start to think about what sounds good to the listener, people often talk about chords that sound consonant or dissonant, right? So where consonant means two notes sound smooth together, and dissonant means two notes sound rough together. So I'm not going to go as far as saying sound good or sound bad, but I'm happy to, but a lot of people, when they say sound good, they mean sort of sound smooth. So people from a variety of different cultures, different musical histories, sort of worldwide, tend to have the same impressions of intervals that sound smooth together if you ask them about smoothness rather than about sort of what sounds pleasurable. So now I'm going to put the phone hopefully not too close to my little piano and show you what I'm talking about. So many people will say that two notes very close together sound rough, so like this. So let me see, I'm going to make this last a little longer. Can you guys hear my rough sound?
Mm-hmm.
Can you guys hear it? Okay, so that was a C and a C sharp, the two closest notes I could get together on the piano, and they sound kind of rough. You almost get a vibrating noise. But if I keep playing that same C, and then I play it in a chord with other notes that are increasingly far apart from it in fundamental frequency, there's kind of a distinct moment when people, again, from a variety of cultures and musical histories, will say, oh yeah, that starts to sound smoother. So you can listen to that experiment now. That's kind of rough still, I think. Usually when I get to that major third, the last pair of notes I played together, that's both a familiar chord in Western music, but also right around the place where people start to say, oh, those two notes go together smoothly in some way. And then there are other particular intervals that people tend to think go together smoothly. The fifth is one of those. And, of course, so is the octave. So what do those particular kinds of intervals have in common? Well, what they have in common is what they're doing to your eardrum when the sounds come to them. So remember that if I'm just playing one note, what you hear is one pitch, like the C by itself, really I'm not just shaking the air at one frequency, I'm actually shaking the air at that frequency and all of its harmonics. So if that C, let's say, is at about 200 hertz, then your ear is getting shaken at 200 hertz and at 400 hertz and at 600 hertz and at 800 hertz. Now, the way your ear works, and this is talked about a little bit in the second lecture, the way your ear works is it actually maps different frequencies of vibration onto different places on a little membrane. So you can think of the membrane kind of like the membrane in your ear as kind of like a ruler that's thick at one end and thin at the other. And high notes shake the thin end very well, and low notes shake the thick end very well. So if there's let's say the C by itself is shaking the air at 200 hertz and 400 hertz and 600 hertz and 800 hertz, each of those frequencies will shake a different part of the membrane in your ear. So there's a little map, and there's all those different regions are shaking. Okay, so now you want to be imagining the membrane like as a floppy ruler, I guess. And I'm playing just the C, and there are those, let's say, those four regions shaking at 200 hertz, 400 hertz, 600 hertz, 800 hertz. Okay, so that's what's happening. Now let's say I play the C that's exactly one octave above. So I play this C and the one above. Now what an octave means in terms of frequency is that you're shaking things exactly twice as fast. So if the lower note corresponds to 200 hertz and all of the multiples of 200 hertz, the upper octave will correspond to 400 hertz and all of the multiples of 400 hertz. Okay? So now the lower note is shaking the spots in your ear's membrane for 200, 400, 600, 800, and the upper note is shaking the spots in your ear's membrane that belong to 400, 800, 1200, 1600, right? All the multiples of 400. And if you think about it, all the multiples of 400 are also already multiples of 200, right? So there's no new place in your ear that's being shaken by the upper octaves, by this note, that weren't already being shaken by this note. Right? So when we play those two together, we're actually only shaking the very same places, maybe with different amplitudes, but we're only shaking the very same places for the high note as for the low note. So the sounds that people tend to pick out as being particularly smooth sounding together are ones where the frequencies that correspond to the lowest frequency that belongs to that note are simple multiples of one another. So for an octave, the low note and the high note are just a factor of 2 different in frequency, say 200 and 400. For that musical fifth that I played before, this one, the high note is exactly 1.5 times the frequency of the low note, or 3.5 times the frequency of the low note. And that has the same kind of effect in the eardrum. There are a few new parts of the eardrum membrane that are shaken, not the eardrum, the ear's membrane that are shaken by the higher note, but not very many. When you put two notes really close together that make that really rough sound, like these two, those two notes shake areas of the membrane in your ear that are so close together that they're really right on top of each other. So the best theory that people have at the moment for why those two notes sound rough together is that they're trying to shake areas of the ear's membrane that are essentially overlapping. So there's one part of your ear that's trying to shake up and down both 200 times a second and also 205 times a second. And what you get then in that part of the membrane is sort of a jumbly shaking that's neither at 200 nor at 205, but something that's kind of a mess. And so that jumbly shaking that's not just smooth, repetitive vibration comes to your brain as something that seems to be rough. So the smooth intervals are ones where the vibrations are well separated and the new note is not really shaking any new areas of the membrane. And the rough intervals are ones where the same area of the membrane or overlapping areas of the membrane are trying to shake at slightly different frequencies. Does that answer your question?
Yeah, it's like the ear's membrane doesn't have the fine resolution to discern the difference at the quote jumbled.
That's exactly right, and that's exactly right. In fact, the hard part about doing the science of asking this question is that little membrane is hidden inside your cochlea, which is a very stiff, bony structure inside the skull. So you would think that the easy way to do this measurement would be to sort of, grab the little membrane out of some experimental creature if you were feeling cruel and, try playing notes at it and see physically how it shakes, right, and see if this theory that if the two notes are very close together, they shake really the same part of the membrane is the case. But unfortunately, the membranes don't survive being removed from the creature at all, so you can't do the experiment on actual membranes. So all of our understanding really is how this membrane probably operates and probably responds to being shaken at different frequencies comes from trying to do experiments on actual living people with very particular sound stimuli and extracting like what they can hear or what under what circumstances can they tell or discern that two notes are slightly different in pitch, which is called a just noticeable difference. Like you said, it has to do with the resolution, right? How far apart do they have to be in frequency before we can tell that they're different? And people have done a whole bunch of different experiments on this, some of which have to do with playing the notes in different sequences and playing the notes with some other note in between to try to extract what parts of our response have to do with the physiology of that membrane, and as you said, its resolution for telling fine pitch differences, and what parts of our response have to do with our brain processing that information, which is obviously a different and probably more complicated system to understand. So everything we know about this actually pretty much comes from asking people what they hear and then trying to figure out clever ways to ask that question. So I think those were the main questions that people had come up with to begin with. So I'd be happy to answer other questions that people had in mind.
I've got one.
Okay,
Is that
Rob.
right? Just again, the fundamental wavelength, if you're talking about, say, a cello string, is twice the string length.
Yes.
Can you just remind me why that's the case? I'm thinking about a jump rope and not being able to envision why it is that you need
twice.
Yeah.
Okay, great. Yeah. So the wavelength is defined as the distance between two identical places on the string. Okay, so think about your jump rope. That's a great analogy. So you're holding it at either end, right? You're holding it. Let's say you have perfectly strong people holding it either end, so the ends can't move, right? So the simplest thing that jump rope could be doing is making a whole arc where the two ends are fixed and the middle is going up and down the most. Agreed? So what would I say the wavelength of that vibration would be? So the wavelength is the distance between two identical places. Now you might say, well, the two ends are fixed. Those two seem identical to me, right? So that seems like it's kind of the distance between the people, right, which is basically the length of the rope. But that's not quite right, because if you imagine the rope when it's arced up like a rainbow as far up as it can be, right? It goes up and then it comes down. So at one end, the rope is fixed and it's pointed upward, And at the other end, the rope is fixed and it's pointed downwards, right? So those are not identical, okay? So what I would mean by identical is if you imagine that perfect rainbow that goes up and comes down, to get a full wave, I'd have to keep going. Imagine that I would keep going down through the person who's holding it, and imagine that rainbow reflected now so that it's fixed at one end and now it arcs down and comes back up, right? So the identical point, if I could imagine the whole wave, to get to the next identical point, I have to go up and come back to zero, and then go down and come back up to zero, and now I've got a whole wave. Okay, so that arc that you see that looks just like a rainbow is half a wave to me. So the full wavelength is twice that. Does that help?
Absolutely.
Good. Other questions?
Yes. So, Sarah, this is Dave, when you started out, you talked about a tube, your voice being a tube, and it's open at the end. So,
right.
Is that 2 times the length also, or would that be 4 times?
So that's a great question. So obviously you have some control over where things are open and closed in your voice. But if you have a tube with 2 open ends, like a straw that you were going to try to play at a restaurant because you were bored waiting for your food. So if you have a tube with 2 open ends like that, it actually does act exactly like a string with 2 fixed ends, the question that Rob asked. And here's the reason. You can think of sound as a wave of pressure, of air pressure, where when you've squished the air molecules together, the pressure is a little higher, and when you've stretched them out and made them further apart, the air pressure is a little lower. So now if you think about your straw, let's say, right, at either end of the straw, it's open to the room, right? And the room pretty much has a fixed air pressure, just whatever the weatherman says the air pressure is today, right? So whatever the big pressure in the room is pretty much fixes the pressure at the end of the tube. So the ends of the tube are fixed for pressure, and what you want to imagine is the lowest frequency, the longest wavelength wave that could exist inside that straw is one where the pressure is just fixed at the regular resting room pressure at either end of the tube, and then the pressure in the very center of the straw is going from a maximum that's above room pressure, regular resting air pressure, at one instant, and then below the regular resting air pressure at the next instant, just like Rob's jump rope goes up high in one instant and then down low in the next instant. So in fact, yes, if both ends of the tube are open, then the longest wavelength that likes to be resonant with that tube is twice the length of the tube. If you close one end of the tube, then the longest wavelength you can get is, as you said, 4 times the length of the tube, not twice.
So with your voice, then, if you're considering, your mouth is obviously an open end. Is the other end of the tube, are we considering that to be an open end where, in your lungs, or?
Yeah, you're right. So that's a very good question. So the whole idea of perfect open and closed ends, which have either twice the length or 4 times the length as the longest wavelength, that's a marvelous approximation that works well for violin strings and for almost nothing else. So in fact, even that straw that I was talking about, it can't quite be the case that the pressure is absolutely fixed to the air pressure at the end, so that's a perfectly fixed end, because somehow the sound gets out into the room and gets to your ear. So, it can't quite be that everything's really just fixed and kind of killed off at the ends like that. So all real tubes are not perfectly fixed for pressure, which means perfectly open at both ends. They're all somewhere between being perfectly open and perfectly closed. So the tube that is our voice is pretty open when our mouth is open, and the other end can act more open or more closed, kind of depending on how you're breathing and how you're manipulating the lower part of your vocal tract. So so there's not a simple answer to that. Actually, there's something interesting about that I would love to mention, which is that whether where the end of the tube is actually something that's different for waves of different wavelengths. So if you think again about the trumpet, which is narrow and then gets broader and broader, basically the waves don't notice the end of the waves notice the end of the tube at different points depending on how long they are. So the long wavelengths notice the end of the tube first, and then the shorter wavelengths don't notice it until later. So the actual, for something that has a variable length, a variable width, like your mouse or a trumpet, the actual length, the effective length that the sound wave sees depends on the wavelength of the wave. So the tunings are not as simple as they would be for a string with two fixed ends, for which every vibration of the string sees the ends as fixed in the exact same two places. That's one of the things that you get out of shaping the bell, say, of a trumpet, is shifts in the tuning as well as shifts in the harmonic spectrum or the sound quality that comes out.
I have a question that might be related to that. I've noticed that in an orchestra or a musical group, if you have really large instruments like tubas or string basses, it seems like it takes a little longer for them to start generating the tone. In other words, the conductor will give the beat, and the piccolo comes in right away.
Right.
But it almost seems like the bass player has to start moving his bow an instant earlier if he wants the sound to be heard, together with the whole orchestra. Is that because it takes a while for the instrument to start that wavelength to start vibrating?
That's actually a great question, and that's a really good insight. So both the string bass and the tuba, which my son plays, and every other kind of instrument, they're funny if you're bowing the string bass, right? You're sort of pulling on it continuously, right? You pull it for a long time to the left, and then you turn the bow around, and you pull it for a long time to the right, right? And yet somehow we think we're setting up some kind of repetitive vibration on the string that's sloshing back and forth much more often than the bow, right? The bow might go back, change direction every 10 seconds, right? But somehow the string is sloshing back and forth maybe 100 times a second in order to generate those low notes that you hear. That's their frequency, about 100 times a second. So for the bow to set up that vibration, what it actually has to do is it pulls the string a little bit. The string sticks to the bow, and then eventually the string will slip back, so it's almost like the bow is plucking it, and then that pulse that you've created on the string bounces to the end of the string where it's fixed, bounces off the end, comes back, hits the bow, and catches again, and then it gets pulled a little more, which is like plucking it again, and then that bounce goes off and comes back and recombines with the other bounce, and eventually those multiple reflected bounces build up the vibrating wave that's periodic, that's creating the sound that you hear. So you're absolutely right that there's a sound buildup, and you're also right that building up that sound on a really large instrument takes longer, because if you compare like a violin to a bass, right, on the violin, that initial little pluck or pulse that you created on the string only has to get to the end of the violin and come back before you kind of get to start building up a sound made of multiple plucks. Whereas on the bass, it has to get all the way to the end of the bass string and come back, and that is definitely further. So you're right about that. And there's something a little bit more complicated but equivalent that happens in brass instruments, where you're sort of blowing on it continually, and there are waves bouncing back and forth, and they're sort of combining with the vibration of the lips to put together a periodic sound that's oscillating in the tube that would be either the trumpet or the tuba for a lower instrument. So yeah, it takes a little while for that sound wave to build up, and it makes sense that it would take longer in a larger instrument because it's built up out of reflections coming from the original source of the vibration to the end of the instrument and then back.
Interesting.
Yeah. Excellent. Are there one or two more questions that anybody would like to ask?
Do all vibrations in nature produce sound regardless of the medium, even though we can't hear most of them?
Aha. So there's two great questions there. So producing sound and us being able to hear the sound, as you said, are separate. So, yes, so any physical vibration of stuff we think of as a sound wave. So if I shake the molecules in your desk here, I'm sitting at Rob's desk. So if I shake the molecules in the wood of your desk here, they'll shake the ones next to them, and they'll shake the ones next to them because they're all connected together by electrical interactions, and that is a sound wave moving along. And when it gets to the end, or the top, or the bottom, that shaking of the molecules will shake the air around us and create some vibration of the air, and that is also a sound wave. And if it's between a frequency of about 20 hertz and 20,000 hertz, you'll hear it. Now, suppose we put your desk in the vacuum of space. I hope that'd be all right with you. So if we did that and I thwacked the desk, I would still get the molecules in the desk shaking, right? But nobody would be able to hear that sound who was across the room because there would be no air molecules to shake and carry that vibration to your ear. So there's the creation of the sound, and then there's the carrying of the sound, which requires that there be something in the intervening space. Right? And that's actually, the denser the something is, the better the sound is carried. So this is why people worry about whales getting their ears damaged in water when we make very loud sounds in the water, maybe more so than we would by the same kind of loudness, initial loudness of sound coming to you through the air, which is a less dense medium that carries sound less effectively just because the air molecules don't run into each other as completely as water molecules do in a liquid where they're closer to one another. You didn't ask that, but that's okay. Good. Well, I hope that it's been interesting and useful for you. It's been great to have a chance to talk with you all and answer your questions about musical sound.